dropping okay. And also because the symmetry actually comes from dropping the UV term, the frequency term here, and the symmetry. If you actually go to the high energy limit of the theory, the conformal symmetry is actually also explicitly broken. And the consequence of this kind of spontaneously and explicitly broken time reparameterization symmetry is that the time reparameterization has become effectively the Nambu Goldstone mode of the SYK model. However, the SYK model that I have just talked about is a 0+1D model. Means that the system that does not know about space. It only has a time dimension. So in recent years there has been many effort in trying to generalize the SYK model into some higher dimensional setting, meaning that to put this SYK model onto a realistic lattice. So here are some works that has tried to do that, and all these papers are basically doing the following. They try to make a lattice of the SYK islands. Means that at each lattice site there is a quantum dot. In this quantum dot there are many. There's one SYK model, and then they can interact within this quantum dot through the random Gaussian couplings. And then the perturbation you add to this SYK model is to add some hopping turns into this lattice. So there are two ways. There are usually two ways to do this. So first thing is to make this hopping turn TAB a constant. That is, you have some translation symmetry. And then the other way is to say these TABs are also Gaussian random variables, and then make the system random. But then at the end of the day, it doesn't matter how you do that. People usually see the following behaviors in such kind of systems. So first, there is a crossover energy scale that's given by t squared over u, and when your temperature is below this crossover scale, you will get a heavy from liquid behavior. What I mean by heavy from liquid is that if you actually look at the resistivity of the system, it will grow as t squared rather than linear in t. But then if you raise your temperature and you are going above the crossover scale, you actually see linear in t resistivity in your system. But however that looks good because this is the first example to build a linear t resistivity metal from this kind of SYK models. But however, the result is not so perfect because the slope of this linear in t resistivity that does not match the Planckian dissipation pattern. It actually depends on the interaction strengths T and U. So here comes the plan of my talk today. So first I will try to introduce a new model to try to incorporate the Syk model into a lattice, and this work comes from an earlier paper that is shown here. So what we are trying to do here is to use some idea of fractionalization to try to make the hopping term and the interaction term in the lattice Syk model to compete with each other. And then we also propose this theory to be a candidate theory for the quantum phase transition that actually happens at the critical doping in the Cook-based superconductors. And in the second part of my talk, I will try to use some results that you use the sophomore theory for the Syk model to actually derive the linear in T resistivity behavior. So our starting point is the following TJ model that may be familiar to many of you. And what we are trying to do is to assume there are two spins, like so these C's are electron operators and these S are the on-site spin operators. And then the electrons they obey the familiar fermion commutation relations, and then the spins can be decomposed in terms of the fermion operators in this familiar form. And then we will actually look at the whole dope side of the problem, meaning that we assume that the electron filling factor cannot be larger than 1. And therefore, if you look at the Hilbert space of a single lattice side, there are three possible states. Either it's empty or it's filled by spin up or filled by spin down. And then because here the constraint here, the filling is lesser than 1. It's very hard to deal with. So we will try to use the following slave boson technique. That is, we try to fractionalize the electron electron operator into a holon and a spinon, where the charge is assigned to a boson B, and then the spin is assigned to a spinon, which is fermion. We call F alpha. And then when you're performing this kind of fractionalization, there is an emergent U1. There is an emergent U1 gauge symmetry that it is shifting the boson B and the fermion F by the same phase. And then to ensure that you only has 3 states at each lattice site, you actually require the U1 gauge charge of this emergent U1 symmetry to be 1. However, there is also a mathematically equivalent way of doing this fractionalization, is that you make the holon a fermion and then make the spinon a boson. And there is also this familiar U1 gauge symmetry. But of course this 2 ways of dealing with the problem are equivalent because the so-called super algebra SU12 and SU2 are actually the same. However, I should also point out that this kind of what we call super spin language is only a way of it's only a way of bookkeeping the operators in our system. It's actually not a symmetry of our problem. The TJ model does not have supersymmetry because the generators of this supergroup, which is the electron operator C and a spin operator S, they does not commute with the Hamiltonian. So here is the phase diagram of the phase diagram of this fractionalized TJ model. So here when we are starting with a deconfined quantum critical point where those holons and the spinons the holons and the spinons have the same energy. And therefore, by the principle of equal probability, the average filling fraction at the critical point is work out to be 1/3 because because there's a 1/3 probability for the site to be empty. But however, this is only a zeroth order result. And when you're actually working with the theory, you using renormalization, we're actually performing a renormalization group calculation for this problem. You find out that this critical value is heavily normalized.
Sorry, I have a question.
Yes.
When you say zeroth order, zeroth order in what small parameter?
It's zeroth order in some kind of epsilon, expansion. So the calculation is in another paper. So basically, what you do is to try to map the TJ model into some kind of single site impurity problem, and you try to use do a RG calculation to see if there is any any fixed point with one relevant direction. And then what I mean zeroth order is the zeroth order is the lowest order in the epsilon expansion or in the epsilon expansion of the RG calculation.
Sorry, what is epsilon?
Yeah. Okay, so I actually don't have the slides here, so let me try to explain that. So basically what you're trying to do is to try to assume that we basically assume that at the criticality, the spin correlator and the fermion correlator are actually some kind of power loss. They scale as like 1/tau to some power. And then there in this power there is and then to try to confirm that whether the critical point is stable or not, we'll try to map the TJ model into a single site impurity problem where those power law behaviors of these correlators can be assigned to some auxiliary fermionic or bosonic paths in some higher dimensions. And then basically we are performing RG analysis for this fermion boson bath problem in some higher dimensions. And then in this RG analysis you can do some power counting procedure to find some marginal couplings, and then from that you can get some small parameter. You can get some small parameter epsilon from that.
Sorry. I mean, you map this TJ model into a single impurity problem coupled with a bath. I
Yes.
guess that epsilon is some decaying power of some modes in the bath. But shouldn't that decay power be determined self-consistently in your theory instead of as a instead of being treated as an input parameter?
Oh yeah, it's actually determined. Self-consistently. It's like we will assume that there is some power, and then we use that power to fit into the model to compute the correlator, and then we require that the correlator we compute it's actually consistent with the assumption that we put in. And then from that way you can determine the decaying powers of these correlators. Does that answer your question?
Oh yeah. Please go ahead. Yeah, continue. Okay.
So the intuitive picture of the intuitive picture of the TJ model phase diagram, and then is that when you are putting when you're tuning the doping P, you're actually changing the energy between those fermionic states and the bosonic states. And then on the right hand side, it actually turns out the bosonic holons will have lower energies, and therefore it is preferable to actually condense these holons. And then when we condense these holons, the fermionic spinons will actually look like the physical electrons. And here what you get is because it condense the holons, because the electron is the same as the fermionic spinons. The filling factor here is actually 1 minus P. Because if you assume some kind there is a Hubbard model that's underlying this, then the 1 plus P is the same as 1 minus P that is related by a particle Hall transformation. And here the electrons in this space will actually behave like a disordered Fermi liquid, and then the spin correlator is actually goes like a 1/tau squared. And then on the other side of the theory, it turns out that the bosonic spinons will actually has lower energy. Therefore, it's more preferable to actually condense this bosonic spinons. And therefore, the charge carriers will actually become the fermionic holons, where the charge carrier density is actually P. And this space is a spin glass because the spinons are condensed, and the spin correlator is actually constant. And also, I want to mention that this kind of fractionalization approach can actually fit into a greater framework, which is the random TJU model. So the TJ model that I have just discussed is the limit where the Hubbard U interaction is actually the strong interaction limit of the Hubbard U term. Where we are looking basically we are looking at a point where my mouse is pointing here, where the Hubbard U is actually infinite. But however, if you assume that the Hubbard U term can be finite, you can actually try to extrapolate the quantum critical point into the UP plane, and then it will intercept the US's as on zero doping point, and at this point there will be a metal insulator transition that belongs to the SYK criticality class. And here is a recent numerical work that has started the metal insulator transition that has just described, and what I found in their numerics is that they found that the spin ring correlator will actually decay like 1/10, which is what we predicted in our deconfined critical point. And also they found that the resistivity is actually a linear function in T, and then it's with a very small residual resistivity at zero temperature. And then in the following paper, there is actually we actually try to map that problem to the SYK criticality. And what's next? I will try to describe a large Z and a large Z and large M limit of the TJ model. So what we'll try to do is the following: we will try to enlarge the spin symmetry into SUM, but also to make the hopping terms the T term comparable with the J term. We will also need to enlarge we'll also need to put in some orbital symmetry, which is SUM prime, and that means we'll assign another index L to the electron operators, and we'll be taking the large N limit of M and M prime, such that the ratio between M prime and M are actually fixed. So we will be using the SUM prime M approach. That is the holon is a boson, and then the spinon is a fermion. You can do it in the other way, but it is completely equivalent. And then we also have the familiar U1 the emergent U1 gauge symmetries for the holons and the spinons. And then we also will fix the gauge charge in the large N limit. And also we try to fix the doping density by introducing some chemical potential for the holons. So we will try to put this TJ model for simplicity. We'll first do a large Z limit of our problem. When I say large Z limit, I mean I put it on a I put a theory on a beta lattice with Z neighbors where Z goes to infinity, and And there, another way of saying this is that we are doing some kind of dynamical mean field approximation for our problem. And then in this problem, we'll take the hopping term Tij to be a constant. But we will assume that the spin-spin interaction Jij to be some Gaussian random variables. And then the first step you do in this in this large Z limit is try to decouple the problem into a single side problem, where you self-consistently introduce some electron Green's function and the spin Green's function, and then you will try to solve that model self-consistently such that the electron correlator you compute from that theory actually agrees with what you assumed. So the second step is to perform the large N limit, and after doing the large N limit, you will assume the following type of a saddle point equation. Okay, so I just speed up. So you will get a following type of a large N SYK type saddle point. And this SYK saddle point has a U1 gauge symmetry and also the tire reparameterization symmetry. And then in the infrared, the solution will be given by 4 parameters. So there are some normalization constants C and some theta angles. The physical meaning of this theta angle is actually given by is actually the U1 charge of these bosons and fermions. And it can be fixed it can be related to the UV charge by the following Larginger constraint. And okay, so there are some. Okay, let me skip this. And to get a transport, you just there's some standard way to write down the full Green's function from of the problem on the beta lattice from the single side Green's function. And you can actually write down the Guo formula for this problem. And then at zeroth order of that problem, the scaling dimension of those fermions and bosons are all 1/4. And then from some dimensional analysis, you'll find that the conductivity you compute from that is actually a constant, is T independent. So therefore, the next step we need to do is to try to include some corrections to this conformal symmetry. And the result turns out actually to be linear in T. So I want to, and to be honest, that the correction, the linear in T correction that we compute here is actually much smaller than the background term, and we believe that it is to be some artifact of the large M limit.
Sorry. Can you remind me of something? Actually, normally, if we take the SYK model, we calculate conductivity. That's already a linear T. So what's different here? Okay,
because there you're only dealing you are solving the XYK model for like electron for the electron operator. It's the scaling dimension of the electron is 1/4. But here we have fractionalized the electron into a spin-on.
But the current let's see. But since F does not carry any charge, so shouldn't the charge? Sorry, the current operator should only involve B operator, right?
The current operator is written using the electron operator. So when you are computing the conductivity, you should use the electron Green's function, which has scaling dimension 1/2.
Yeah, I'm just thinking. Suppose I want to calculate the spin-spin correlation, right? I mean, I will only be using like the correlation function of F, not like C. because B does not carry any spin.
But the problem is of only using F or B is that they will not be U1 gauge invariant, because when we are doing the fractionalization.
So for example, for the spin operator, right? F dagger sigma F, that's still U1 gauge invariant.
Yeah,
right?
for the yes.
Yeah, so
for
I don't need B at all.
Can I comment here? Haoyu, sorry, excuse me.
Yeah.
I think the difference is the old SYK model. First of you're just dealing with electrons only, and the hopping operator. Right? I actually love you said it. You said it right. Is just a bilinear in the electron. So it decays as 1 over square root of tau, whereas here it's electron itself is 1 over tau. And also, this is not, what I really wanted to say was, this is not perturbative in the hopping. It depends on the density of states. Yeah.
Uh-huh.
Yeah, sorry.
Yeah, sure. I mean, I'm just confused by something very, very simple, right? So, I mean, if I take the calculate spin correlation, I don't need to use a spin. I mean, I don't need to use the electron operator. I just need to use F, because F dagger F is already a gauge invariant operator.
Yeah.
So I can just use the F correlation function. I don't need to use the B correlation function. But if you calculate current correlation, I have to use both F and B. I'm just confused about the difference between like the spin operator and the current operator, and how, I mean, and what kind of Green's function we should use.
Yeah, well, you're not condensing the B's here, or none of them have been condensed, so you have to use the gauge invariant combination. Mm-hmm. That's important here. None of them, they're both uncondensed, the F and the B.
Okay.
It's sort of, in this large dimension limit, there is no gauge field, but effectively you have to use the full Green's function, which in some sense is including the full gauge field correction. Uh-huh. It's not an independent degree of freedom.
Okay.
Okay, so let me rush through how to actually include the corrections from the conformal solution. So the key is to consider the broken reparameterization symmetry in our problem. So it is spontaneously broken down to this fractional linear transformation, the group SL2R, and also it's also broken by the UV source terms in the saddle point equations. And then there are two consequences of this broken symmetry. So first, there will be some irrelevant corrections to the Green's function, and second, the low energy fluctuations will be dominated by those reparameterization modes, because they are the Nambu-Goldstone modes. And then the coefficients here is alpha G and alpha S are actually related because they actually come from the same source. So here is a G sigma action that actually reproduces the saddle point. So what you do is you try to define the self-energy to separate the IR part of your theory and the UV part of your theory. So what I have introduced here, some sigma terms are actually the UV sources, the frequency terms in the saddle point equation. And the intuition for this for working out these corrections is try to separate your time scale, the problem, into two time scales. One is the UV scales is basically given by the interaction J, and the IR scales is given by the temperature. And then what we have is some kind of a renormalization picture in mind. Is that the effect of the UV term is to introduce some dimension fold couplings into your problems, like in the following way. And here the operators OH, there are some operators that actually appears in the OPE of those spin-ons and holons. And therefore, from that you can just compute the corrections from the following 3-point functions of delta, and H. and therefore the corrections to the conformality will have the following power law form. And then here the operators that actually appear in this OPE can be worked out by looking at the 4-point functions, and here are the results. So first is that at h equals 1, there are two operators, QB and QF. They actually corresponds to the U1 charges of the bosons and fermions. And the next operator is due to the time reparameterization symmetry, which is actually which can be identified as the energy operators or the Schwarzian or the Schwarzian term in the Syk model. And here we can work out the form of the corrections up to some multiplicative constant alpha g, and then this alpha g actually depends on the UV detail, and to get it you actually need to fit the numerics. And there are also some higher dimensional operators that is less relevant, and we will not discuss it here. So therefore, the h equals 1 corrections it only makes it almost a charge in your problem. The charge is already given by the theta parameter, so you just need to redefine the theta parameter. So the leading corrections is actually given from the Schwarzian term, and then the result is that the conductivity will be corrected by some power of a T over J. And then therefore, if you invert the conductivity, assuming that the correction term is small, you'll get a linear in T resistivity. Another thing I want to mention is that the Schwarzian term is also related to the heat capacity in this SYK type of models. So therefore, we actually say that there is some universal relation between the slope of the linear resistivity and the slope of the heat capacity. And also, okay, so here are some final remarks for this work. Sorry, I said something wrong there. So actually, the residual resistivity rho of 0 is actually related to the 1/tau decay of electron Green's function, and this 1/tau decay of this 1/tau statement of the electron Green's function is actually non-perturbative. It is also very verified in some small n calculations. So we express such a term will always be there.
Yeah, sorry. Can I have another question? So normally, like, so when we calculate a 4-point function in the Syk model, I mean the Schwarzian correction will be at the 1 of n order, n being the n in Syk. So here it seems like you have order 1 correction.
Because
right.
Here we are actually not computing. We are not computing fluctuations. We are just computing the corrections to the Green's function. It's and I think in the original Syk model, if you look at those corrections, it's higher order in not 1/beta j, but it's the same order in n.
I see. Okay. Mm-hmm.
So the second remark is that this linear power in T is not some trivial consequence of Taylor expansion. It's actually pinned down by the scaling dimension or scaling dimension of the Schwarzian term in the Syk model. So therefore, we also believe that such a linear in T power can actually be generalized to small n series and other critical models when there is a time reparameterization symmetry. And also this mechanism is somewhat universal because the time reparameterization actually couples to all degrees of freedom. And in the in the holographic context, this corresponds to gravity. Therefore, it comes to everything. So it is universal, and it actually doesn't depend on doesn't depend on the scaling dimensions of your field contents. You can try to you can consider some other series where the fermions and bosons have some different scaling dimensions, but this linear resistivity will still be there. And finally, the relation, the universal relation between the resistivity and the heat capacity that we derive here actually depends on the large N limit, because it depends on how the electron Green's function depends on momentum in the large N limit. Because here in the large N limit, the electron Green's function is actually momentum independent. But for smaller m's, the details of the band structures may be important. Okay. I think this is all from my talk. Thank you for your attention. Is there any more questions?
Thanks, Haoyu, for the nice talk. A bunch of questions, but maybe we could take one or two more and then wrap up.
Here's a question.
Yes.
Do we know, or is there an estimate of how big the linear range is? As in, that linear T is, you could say, the first order correction in the conformal perturbation theory sense, but I presume other operators will come in and produce corrections that are of other powers of T, and then those will sort of makes it nonlinear. Do we know how big a window do we have for the linear?
Okay, so all the corrections to the conformal solution will be organized in powers of 1 over beta J. So I think it's at the temperature order of J or T, of the hopping term or the spin interaction term.
Right. So what's the window then, in terms of your saying?
Well, that's going to require some numerical solution of these large N equations. And that's in progress.
Oh, okay. I see. Thanks.
Yeah. Yeah.
Okay.
Also, I have another comment. I thought a bit more about Chenke's question, and I put some comments in the chat.
I have a question.
Yes.
I'm a little confused about the larger picture, in particular with regard to superconductivity. So in the experimental data that you showed at the beginning, where the linear T goes all the way down to very low temperatures, I presume it's because it's in a magnetic field. Is that correct?
Yeah.
So,
I think this is the case.
So whereas in the model, it seems to me that the thing that's suppressing superconductivity is the large D limit, this ultra local limit that you're taking.
Yeah. We are not considering any. Yeah.
Well, there's also the fact that the exchange interactions are completely random. There's no uniform component of the exchange interaction.
Mm-hmm.
Which is related to Haoyu's answer, of course. I mean, the large D limit is simpler when you have just fully random exchange interactions.
Thanks.
Okay, why don't we call it here. Thanks again for the talk, Haoyu, and everyone look out for the next email from Hassan about the next talk. Take care.